As soon as I was like, does everyone hear me? Someone exited. Hear the sound. Okay, all right. Let's get this thing started. Hello, everyone. Hopefully you are fine. Well, not lots of updates, but we do have some updates to go over to make sure that everyone heard the news. As always, let me turn off the video here just to make sure we minimize any potential issues. So the math final, we know the date now. So math final, Thursday, May 21st. It will be from 3:30 p.m. to 5:45. Okay. Let's see here. Now, I know that some of you are telling me that you have conflicts, and some of you are telling me that you had like 3 finals in a day. Just so you know, I wouldn't call it official, but it's been practiced like this forever. But the policy is that you can have the middle final removed and rescheduled for another day. And how you'd go about this is you'd actually reach out to the instructor for that course. So far, everyone who's told me that they have such a conflict, the math one happens to be the last final that day. So it's not really my problem. You have to reach out to your other instructor. So that's customarily what is done. It's been done that way forever. It's even on, if you go to the final exam schedule online, you will see, if you go to the section, there's a section called Important Instruction for Faculty. And then there's a bullet point under there that pretty much says, if a student has 3 finals on one day, then they can opt to have the middle one, take a makeup for the middle one. So yeah, so just so you know, that is an option, and you should reach out to your instructor for the middle final. Final is on Blackboard, as you guys know. More information on that, I don't really know, but I do know it's not going to be long form, so it's going to be multiple choice and or short answer and or something like matching graphs and equations, stuff like that. So it's going to be things that you can do in short form and you don't really have to show your work. But yeah, other than that, we do have a practice run on Blackboard, which we'll also do on Friday. So for Friday, we're going to finish up partial derivatives. We're going to start and finish partial derivatives. And we are going to actually do this trial run in Blackboard. So I want us to do like a sample test in Blackboard. And it's not going to be specifically relevant to the class. It's just 4 random math problems. It's a 10-minute test, but I want you to have the feel of actually going to Blackboard, accessing a test, doing a test, and then submitting the test, just so you can see what it would feel like. Of course, your test is going to be a lot longer than this one, but just to make sure that everyone can log into their Blackboard, they can find the test, they can actually take it and submit it. We're going to do a trial run of that. So that's for Friday. So Friday is going to be a lot of fun. We're going to do partial derivatives. We are going to do the Blackboard practice. And with that, we would actually end all the topics that I wanted to do for the syllabus. Well, not what I wanted to do, well, what I required to do. We actually did a little bit more than is required of us in the syllabus. So, you know, it's the way I like it. I like my kids to kind of have an edge over all the other kids. So you guys learn everything I taught you. You guys are not only good enough to pass the final, but you're better than all the other Calc 2 kids, which is how I like it. Now, today we're going to finish up limits, and I'm trying to think, was there another announcement that I had? I think, and I was looking at, I'll definitely send out a finalized email today, but when I was looking at, let me see if I can find it. When I was looking at the doodle poll that I sent out, it seems that the makeup class for this Friday will be a little bit earlier than it was last time. So it seems like most people are somewhere in like the 2 to 4 p.m. range, last I checked. Let's see, is that still the case? That is still the case. So last Friday we had class from like 4 to 6. Seems like most votes this time around were in the 2 to 4 range. I think we can pretty much get that set now. Homework due date, why would you need it extended? It's all the way to like next Friday. Next test is Thursday, next week Thursday. I know. I would try to get through the homework because after the homework is due on Friday this week and your final is actually the following week. I don't really want you spending time doing homework in finals week. I want you actually prepping for the final. So I don't know. At the moment, I don't want to extend it. Try your best to get through this. We'll revisit this early next week, but I don't think I would extend it. Because I really want you to be focusing on the final for finals week and just reviewing everything. Yeah. So I think I'm gonna call it right now. We've had a couple days to say, so class Friday, 5/8, 2 to 4 p.m. And it will be the last class for new material. Okay, once we get through that, we'll finish everything. And yes, to remind you of the homework policy, it is still the case that if you get 85% of everything, you score 85% on average, I'll actually bump that up to 100%. So you don't even have to be perfect with the homework. If there's one like homework problem that's really annoying and you tried like 53 attempts, yeah, just probably forget it at this point. It's much, it's going to be better for you to spend that extra time practicing for the final or practicing the mock test that I gave you guys. Okay, and in regards to the mock test, so our test is next Thursday. I will post a review for that mock test. Again, an online version tonight, maybe leading into early tomorrow. Yeah, so I think that's done with the administrative stuff. So our final definitely set in stone, Thursday, May 21st. If you have 3 finals on a day, you're allowed to move the middle one. You need to contact the instructor to get that done. We have class Friday, as in tomorrow, 2 to 4, last day for new material. And we're gonna cover partial derivatives, and we're also going to do a Blackboard test run through so that you're not lost on final exam day where to go and how things are gonna work. And I'm gonna set up that test to follow the rules as to how the final is going to be set up. So from what I'm hearing, in the online final, it's not going to be as easy as you would think, because in one sense, you're not going to be allowed to like look over stuff, from what I understand. So once you do like problem 1, you move on, you cannot go back to problem 1. So you have to kind of get it right the first time is the kind of thing. So on one hand, while for some people, multiple choice might be easier, it's not going to be easier in the sense that it's going to be more like one of Jhevon's quizzes. So as luck would have it, studying for my quizzes was a good prep for this, because you got to be perfect the first time. So yeah. So just so you know how that's going to feel, we are going to run through that on Friday. Hopefully I'll have students from both sections. I will leave that test open longer, but I would like you guys to go through it with me in real time. I'll give you guys like a 10 minutes and you give me feedback on anything that is working or not. Okay. All right, so let's jump into this. We shouldn't take the full time. I kind of rambled on a lot in the last class, so I didn't get to partial derivatives for them, so I'm not going to do it for you guys. So if we get to the point, we should actually get through, because even with that, I finished the lecture in like an hour and a half, so we finished 10 minutes early. So I think if I restrict myself from rambling too much, we can get through this maybe even slightly quicker than that. So let's actually just jump into it so that Ash can go back and try to catch them all. All right. So last time we were talking about limits. Now, in many ways, how we think about limits is exactly how we thought about it in, I think he said review for next Tuesday. Wait, what is that? Oh yeah, so Tuesday's class would be review. So
is it review for the whole chapter or just for the exam too?
I guess we can start. I'm willing to review anything from the beginning, but I guess we would want to start by reviewing things from the second half so that you're prepared for the test on Thursday. But I'd be open to anything. And because the next week's class is going to be review, it's likely that the Monday and Wednesday class will be completely different. So you might, if you can join the Monday class as well, that would probably be to your benefit, because a lot of it is going to be me reacting to questions from you guys. So the Monday class might ask different questions than the Tuesday class. So next week's classes should be different. So you can actually go into both of them. Anyway, so let's go into limits. A lot of things are the same way that we knew it. So the limit properties are the same. So the limit of a sum is the same as the sum of the limits. Limits pass through continuous functions, all that good stuff. Whenever we're in the right situation, we can still use L'Hopital's rule and things like that. We're going to see some examples of that today. And the limit is just kind of tracking the output once your input is doing something. So the limit is the number that the output approaches when your input approaches some other number. The difference is in multivariable calc, our input is a coordinate that is approaching some coordinate. And then you are going to try to see what is the output, or the Z value, oftentimes, if it's a two variable function. What is the Z value approaching as the coordinate approaches something else? One thing that is different is that in single variable calculus, you only had two directions to concern yourself with: limit coming from the left and limit coming from the right. If both of these guys match up, we say the limit exists and it is their common value. In 3 space though, when your inputs live in 2 space, this is no longer the case. You can approach a point from an infinite number of directions along an infinite number of curves. So to be able to talk about the limit existing, you would have to, in theory, be able to check an infinite number of directions approaching a point. Now, we are going to talk about how to get that done today. But before we did that, we learned how to look at when a limit does not exist. And these steps are very, very important. I will also mention, now you should also remember limit strategies from Calc 1, because they can and do show up. And so when I was teaching my class Calc 1, I gave them a set of strategies for limits back then. And so there was a set of steps that you, certain things you do first, certain things you do second, certain things you do third, etc. So for example, you always try to plug in the number first, see if you can get an answer. If you can't plug in, try to simplify to see if you can plug in, usually like factoring and cancel or stuff like that. If you can't do that, you can look at graphs. If you can't do that, you can try to apply a special technique, like a special trig limit or limits at infinity of rational functions and things of that sort. You can do tables of values. So there's a whole list of strategies that we had for single variable limits. You need to remember those. I'm not going to go over them. You can rewatch my 201 videos on limits if you want to go over those. But we had some new strategies for the 3-dimensional case. When you want to show that a limit does not exist, all you have to do is show that you can find 2 paths, right? Because an infinite number of paths need to work out and they all need to give you the same answer. The moment you find 2 paths that differ in value, you can show that the limit does not exist, because if 2 of them don't agree, then of course all infinite directions won't agree. The first thing you try to choose is the obvious path. And this is when all your Calc 1 things don't work out, when you can't plug in, when you can't do all that stuff. It's not clear that you can just plug in the number and get an answer. It's indeterminate or something else. Try the obvious path. So if you're taking the limit as x comma y approaches a comma b, try going along the path x equals a or y equals b. Try not to be redundant though. If you can kind of eyeball it and see that going along y equals b is going to give you the same result as going along x equals a, don't do it. Just try something else. The next kind of path that you want to try is a path that's going to allow you to simplify things. So as you saw here, we tried x equals 0. We noticed that y equals 0 would give us the same answer, so we don't do it. And we go along x equals y. Why did we go along x equals y? Well, it would allow us to combine terms of the denominator and allow us to cancel things, and we actually got a different result. Also notice that just because infinite paths need to work out for it to work doesn't mean you can choose any path you want. There is such a thing as an invalid path. The paths you choose must pass through the coordinate that you want the limit to go along. So here, if we're going to 0, 0, any path you pick must go through 0, 0. So going along x equals 2, for example, is not a valid path. It does not go through 0, 0. Okay, so choose paths that go through the point. Start out with the obvious ones, get a result, then start choosing paths that allow you to manipulate the symbols that you have there to hopefully simplify and cancel stuff to get another result. Now, once you get 2 different results, limit does not exist. Okay, now we ended last class with a particular example where this guy, and he kind of made a fool out of us because we kept going along paths and we kept getting 0, no matter what, try as we might, kept getting 0. And it turns out that Ash was tricking us with this one and the limit actually existed. So thank you, Ash, for that. So now it turns out this guy existed, and obviously if the limit exists, it will have to be 0 because all the paths would have to agree. And so I'm going to show you how to show that a limit exists, and that it now is the next time. So how do we show this? How do we show a limit exists? How can you examine an infinite number of paths? And I'm going to show you how to answer this question in several different ways in this class, and then we're going to wrap it up. So now, technically speaking, to show that a limit exists, you have to show that this definition is true, the epsilon delta definition. However, it's very annoying to work with that definition, and so we have something that's going to help us out. There is a theorem that we can use that can help us show when a limit exists. Okay, and this is the theorem. Okay, so here's the theorem, and it actually uses the squeeze theorem to help us, and I'm going to show you how that actually works out. Suppose you have a function that is defined arbitrarily close to AB. Of course, you need that for a limit to work out. You need to be able to inch closer and closer to AB. If there exists some other function, g of xy, such that these 2 bullet points hold, f of xy minus L is less than or equal to that function, and at the same time, the limit of that function approaches 0, then we can conclude that the limit of f is L, okay? So just to make sure that we understand some of the finer points here, G, you need to find this function, right? So it's not going to be given to you. So we're going to go through some ways of finding the function in this lecture. You need to find that function. So you're given some limit. You need to find some other function that does these 2 things, okay? Here, what I want you to notice is that L is the proposed limit. So whatever you think the limit is, that is what you're going to plug in place of L, right? So you're going to put in absolute values, f of xy minus L, get that to be less than some other function that you also need to find. What I also want you to be aware of here is you need to take the same limit of G as in the original function. So if you had the limit as xy approaches 1, 2, then you need to take the limit as xy approaches 1, 2 of g. And it needs to get 0. And yes, it's always 0. You always need to get 0. Okay? So that 0 is a specific requirement. Okay? So given some limit, this guy, right? You want to prove that the limit is L. You can do it by finding a function g such that f minus L in absolute values would be less than or equal to that function, and the limit of that function approaches 0. Now, question, why does that even work? Okay, so why does that work? So here's why it works. Suppose we could find such a g. Oh, it's not like you're sure it will always equal 0, but the thing is you need to find a function so that the limit is 0. But we'll get into that. We'll get into how to find a function and making sure that it would have the requirements. Now, if it's the case that it is impossible, like you cannot find a function where that does this and his limit is 0, then what it means is that the limit actually does not exist, and you just didn't try the right path to show that you got a different answer. If the limit exists, there will be a function that gets this to work, right? So suppose we can find such a g. What would that mean? So then we know that if I take the f minus the L, it's less than or equal to g. Well, that would mean this is true, right? Because I can take the absolute value inequality and split it into 2 inequalities in that way. Then what I can do is I can add L to both sides. And then at this point, I can just take the limit. Right now, this is the limit that I want to take of the original. Now, the limit of a sum is the sum of the limits. Now, this guy goes to 0 by assumption because we found the g that does these two things. When I hit the g with a limit, it gives me 0. So now what you have is that we get L minus 0 on this side, and we get L plus 0 on that side. So we end up with the limit of f is between L and L. So this means by the squeeze theorem, if you're less than or equal to L and at the same time you're greater than or equal to L, then you must be L. So the limit of f would have to be L, right? It would have no choice, right? No choice in the matter, right? And this is something that transcends all directions, right? If this didn't work for all directions, then what we know about absolute values is false, which we know it's not false. So by finding such a g that does these things, we are guaranteed to have the limit of f equals L as a consequence of squeeze theorem. So by our ability to actually do what this theorem says we would need to do is the same as our ability to actually prove the limit exists. Let's actually do some examples. So we can kind of see, so we can see this in action. And, oh, wait. Let's do this guy, the guy that made a fool out of us last time. Let's go here, and right now we're gonna end this guy's whole career. Okay, let's do this guy, right? The same guy that we started last time. Let's start there. Okay, so now we think the limit is 0. okay? Let me put this 0 in a different color because I don't want you to, there are going to be zeros all over the place here and I don't want you to mix these up. Once you think the limit is 0, this means we need to show, we're all in this together, we need to show that if I put f, and this guy here is my f of xy. We need to show if I put f minus 0 in absolute values, that it's less than or equal to g of x, where g, the limit of g, is equal to 0. And we need to find this g, right? Okay. So you go into the limit. And remember, as I mentioned, showing that a limit does not exist tends to be easier than showing that one does exist. So if a question is phrased like, determine whether or not the limit exists and prove your answer, you're first going to kind of dive in with the intention of showing that it does not exist. You're going to go along the paths that I mentioned that you should go along. If you get anything, if you get a discrepancy, you know, oh, it does not exist. But let's say you keep getting the same number, then that's going to be the red number that you have here. And now your immediate goal is to be like, okay, I need to put f minus this number in absolute values, and I need to find a function g such that in absolute values it's less than or equal to that function, and the limit of that function is 0. So now you know that that's the goal. So now how do you actually go about finding such a function? So let's start with the setup. So here we have x squared y over x squared plus y squared minus 0. So obviously I can kind of ignore the 0 here. So it's just this. I need to show that this is less than or equal to something where that something actually goes to 0, okay? Now, how do we go about choosing such a thing? And it turns out that this is a skill that we've seen over and over. So back in Calc 1, when we were finding limits using Squeeze Theorem, you actually use this skill. And even in this class, we use this skill when we were doing comparison theorems for integrals and for series. You are basically going to try to manipulate the given function that you have. Whatever this thing inside here simplifies to, you are now going to choose your g based on that function. Your g is going to come from some manipulation of that function. You're going to manipulate it in such a way that you know you're getting something larger. So you can make the denominator smaller, which would make the fraction larger, or you can make the numerator larger, which would make the fraction larger. All those tricks that you know, like if there were trig functions in here, you would try to bound the trig function and all that good stuff. So all those skills are going to come back, something that we need again. However, we want to do these things in such a way that whatever is left over, its limit goes to 0. So it's not just a completely random process, but we're thinking along those lines. So any ideas on how to get something larger here? Okay, so Ash said, let's get rid of the y squared in the denominator. Now that can work because y squared is greater than or equal to 0. As long as your y is not 0, that's actually going to be a positive number. So if I subtract the positive number from the denominator, that actually will give me a larger fraction. Now what's going to happen? You're going to notice the x squares cancel. So the absolute value of y is something that's larger than f minus L in absolute values. And as luck would have it, you take the limit as x, y approaches 0, 0 of this guy, you get 0. So choose this to be g. Then you can conclude the limit of f is equal to 0. Not the 0 from the g, the 0 from the proposed limit, from the original position. whatever number you had put there to get this result, you're going to copy that. So if I had to put a 5 in the place of 0, you just prove that the limit is equal to 5. Okay? And we know this has to work, because if it doesn't work, Squeeze Theorem is wrong. If Squeeze Theorem is wrong, you know, the world blows up. So that is it. That is us proving that the limit exists. So you go in with your f of x minus L, f of x y minus L in absolute values. You simplify that. You find something that's larger than that in such a way that its limit goes to 0. Now, I do want you to appreciate that there are bad choices here. So Ash decided to take away the y squared. Now, you could get something larger by taking away the x squared in the denominator. However, if you were, I want you to realize this, there are bad choices, like in life. Example, taking away the x squared. Now, what would have happened if I had done that? Well, I would have that x squared y over x squared plus y squared. It is indeed true that this is less than or equal to that. That's true. The difference is this guy would simplify to an x squared over y. And as xy approaches 0, 0, what happens to that? Right? That's undefined, right? Or DNE. So by doing that one, this guy cannot work as a G, right? He's not G enough, right? So there are bad choices. You have to choose a choice that not only gets you to the kind of result that you want, but it does so in a very convenient way. It does so in a way that it gets you something bigger, and at the same time, the limit of that thing, you need to know that it goes to 0. Okay? So, yeah, so getting rid of the y squared is a better idea than getting rid of the x squared, right? So there are some nuances to this game. So overall, it's the same kind of tricks that we've been using for a long time, for like a year now, with Squeeze Theorem and with comparison theorems that we've been doing. But we need to make sure that we're doing it in such a way that gets us a convenient result. And that has kind of always been true as well. So with the comparison theorems, you needed to choose something where you know what happened to the series or the integral in order to make a conclusion. In the same way, we need to get a bigger thing such that its limit goes to 0. So hopefully that process is clear. But to kind of make sure, let's do some other examples. So someone tell me how to tackle this one. Let's make that a little bigger. So pretend we get this thing, right? So this is the limit that shows up, and the problem says something like, determined whether or not the limit exists and prove your claim, right? So that's what it says. So this guy shows up on my test. I have no idea whether or not it exists. So my first thought would be, of course, all my Calc 1 limit strategies. So can I just plug in the number? Can I simplify? Blah, 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 right? Can't plug in x and y equals 0 because you get to divide by 0. Can't simplify this anyway without changing the value of the function. So none of that is going to work. So boom, boom. So first thought, try to see if it DNE, right? So now you're going to go along some paths, right? So yeah, got some suggestions along x equals 0. What's going to happen to our limit? Our limit is going to look like, well, 0 over y squared. which is 0. Now, if you go along y equals 0, you get the obvious result because sine of y is in the numerator. And so I would get 0. I'm trying to get this guy to fail, right? So I'm going to do something else. So let's go along y equals x. In that case, the limit is going to look like 2x squared, the God path, yeah, 2x squared over, well, now 3x squared. Now you'd realize the x squares cancel. And you'd be left with the limit of 2/3 sine of x as x is approaching 0, but that again gets you 0. So at this part, suspicious, right? These two paths should have gotten me a good result. They're in the set of strategies that Jhevon gave me. So once I don't get this, I'm like, kind of suspicious now. Maybe it exists. Right? And so we're very efficient. By testing 1 or 2 paths, most 3, you should be able to figure out whether or not the limit does not exist. If it takes you more than 3 tries to figure that out, you're not being very efficient and you're not following the strategies that I gave you last time in this box over here, right? So within 2 or 3 tries, 3 in the worst case scenario, within 2 tries really, you should be able to kind of sniff out whether something does not exist. The moment you try these 2, it's not working out. Now, well, using y equals 0 works, but it is redundant. Yes, it violates step 2. So if you look in the strategies, step 2 says don't be redundant. Don't waste your time. If your goal is to see something different, then plugging in something that would obviously give you the same is a waste of time. Right here, there's a sine y in the numerator, right? So plugging in y equals 0 would give me a 0 in the numerator. It's obviously going to give me the same answer here. So I'm trying not to get that. So I tried something different, y equals x, something that should not give me this, right? And it turns out it gave me the same thing again. At this point, you're like suspicious, maybe it exists. Now, once you assume that it exists, that brings you to the second intention. I probably should have labeled the first thing first intention. Find a G. Okay. Okay. And so now we get into the thing that I just taught you guys today. So at this point, I'll let you guys take it away. So here we have 2x squared sine y over 2x squared plus y squared minus, our guess is 0. This is the proposed L. Now, how do I get that bounded by something else that goes to 0? Right, so this simplifies to 2x squared sine y over 2x squared plus y squared. Okay, that was the guy, right? 2x, yes. All right, find me something larger that approaches 0. Remove the y squared, okay? So if we remove the y squared, we get something less than or equal to, this is 2x squared sine y over 2x squared. Our 2x squares cancel. So we can get sine y, and it turns out sine y is going to, and sine of y approaches 0 as xy approaches 0. So choose G equals sine y, and that means the limit of f is 0, the 0 that we plugged in there. So that limit exists, right? But this is the thought process, okay? So you always try to see if it does not exist first, especially if you're not told. There are times when the question will say, this limit does not exist, prove it. Or they'll say, the limit does exist, prove it. Now, if they tell you ahead of time, if they announce that the limit exists, you immediately go to this process here. If they tell you the limit does not exist, you immediately go to this process here and make sure you get different answers. If they don't tell you, you start off with the D&E process. Try to get it to not work. And if you kind of realize after going through a few of the convenient channels, you keep getting the same answer, get suspicious, and then try to show it exists. Yes, so in answer to Mohammed's question, it depends on the problem. There are problems where it might, like if all the variables were turned around here, like if I had 2y squared sine x plus over 2y squared plus x squared, then the right thing would be to remove the x squared. So yes, in the previous two examples, I removed the y squared, but that's just a coincidence. It's not like you always get rid of the y squared. No, it depends on what you're looking at. Okay, so let's try the other one. Let's try this example right here. Make it a little larger. All right, go. This is you guys. Tell me how to deal with this example here. Let's use paths first. So we want to go along x equals 0 and y equals 0. Not what I would have done. Wait, but you said, okay. You can simplify. Remember what I said before. You can actually simplify this. How can I simplify it? Difference of squares in the top. This is x squared minus y squared times x squared plus y squared over x squared plus y squared. These guys cancel. I just have the limit of the x squared minus y squared. And obviously that goes to 0. Limit proof, right? So a Calc 1 process could actually get this done. Now, you could have gone the other process of what we did, so or less efficiently. So let's say someone only remembers the Calc, the 212 processes, and they don't remember 201, right? So they forget their Calc 1. So this is what I'm talking about. Like, we need 212 for 213. That's a joke we made yesterday. You still need 201. Don't forget your 201. Difference of squares is still a thing, and you can apply it, and it's still valid. If you only look at this from the Calc 2 processes that we covered, then yeah, you would first go along x equals 0. You would realize that your limit behaves like minus y to the 4th over y squared. Well, that would be equal to the limit of minus y squared. That would be 0. And then you might go along y equals 0. What would the limit behave like then? Well, it would behave like the limit of x to the 4th over x squared. That is the limit of x squared. That also gives me 0. Now, you start to get suspicious. And so you jump into, okay, let's look at x to the 4th minus y to the 4th over x squared plus y squared minus 0. That's just x to the 4th minus y to the 4th over x squared plus y squared. And now I need to try to get something bigger. Now you'll realize whether you remove the x's or the y's, it's going to be a problem. removing x squared or y squared from denominator is a problem. You're going to result in a limit that's going to have a 0 in the denominator. And so at this point, hopefully, your thought of difference of squares would get triggered. And you would try this, cancel those. So you get x squared minus y squared. That approach is 0. And so you would say choose G to be that. By Squeeze Theorem, right? But look at how much work we had to do to get that to work out. When, if we just remembered our Calc 1 way of doing things, we could actually get to the answer a lot more efficiently. I know it's an eye-opening example, that's why I chose it. Yeah, all right. Okay, so remember your training, grasshoppers. Right, you can't forget anything. So the stuff you learned in 201, still applicable, right? And at this point, I mean, I'm not emphasizing at this point because we're already past that class, but it's kind of the thing. What went through your mind in 201, which was a big chore for you to go through and you had to go through a checklist, you're kind of expected that all of those things should go through your mind automatically at this point within a couple seconds, and we shouldn't have to emphasize that you need to do it, right? The moment you start looking at a limit, you're automatically, you should, as a knee-jerk reaction, start thinking, can this simplify? Can I just plug in? Right? These are just some knee-jerk reactions. Now, you only pull out the big guns like a squeeze theorem or some multivariable technique when your old fundamental techniques don't work, right? So this one, you can do it the way I was teaching you now, but it's much more efficient to kind of deal with this the way that you would have dealt with it in Calc 1. Yeah. So that is how we can use the squeeze theorem to show that a limit exists, and this is why it works right here. You don't need to know the proof, but I just wanted to justify to you that finding a G that does these two random things, seemingly random things, is the same as being able to prove that a limit exists. Now, I want to show you guys something cool. I mean, everything is cool, but you know, we're gonna have like a crossover, right? Like this is gonna be like Spider-Man meets the MCU. It's gonna be that kind of cool. We are going to go back to polar coordinates, and we're actually going to use those guys to help us find limits. So you might have remembered polar coordinates. Hopefully you guys remember that. Okay, where's this? Polar coordinates. We're going to use polar coordinates to attack multivariable limits. Now, let's lead with a little bit of discussion. Why would this be something we would think? Well, recall from polar coordinates, we had certain equations. We had equations that determine what x and y did. We also had an equation that determined what x squared plus y squared did. What are those equations? What is x in polar coordinates? Right, r cosine theta, and the y was? R sine theta. And what is x squared plus y squared? Good question. No, it's r squared. So that you should have automatically. So r cosine theta, this one is r sine theta. Now, you could actually square both of these, add them together, you get an r squared in common. When you factor it out, you have r squared times cosine squared plus sine squared, which is 1, so you get r squared. But you should just automatically know that x squared plus y squared is r squared. You shouldn't have to go through all that. However, so here's the thing. Because the R is a combination of the X and Y, note, as X comma Y approaches 0, 0, what happens to the R? It's going to approach 0 squared plus 0 squared. So the R is going to approach 0. So I can look at a limit where X comma Y is approaching 0, 0, and I can reimagine this limit in polar coordinates. And the only thing I would have to keep track of is the R value. So now I go from a situation where I'm keeping track of two things to a situation where I'm keeping track of one thing, right? So I kind of enter a situation where single variable techniques become even more relevant, and I can get away with things a lot easier. So, and we can replace X, Y, and X squared plus Y squared with the above. Now it turns out this is often going to be very convenient. So here's the guy again, right? Like I said, we're going to end his whole career. We're going to find another way to attack this guy just to show he ain't nothing, right? We can multiple ways to beat him up, all right? I'm going to use polar coordinates to actually do this. So here's another strategy, right? So this is, again, separate from Squeeze Theorem strategy. You can use this as another strategy. Reimagine the world in terms of polar coordinates. So I'm given this limit. What I can do is switch to polar. Let me put this in. No, this thing is misbehaving. It does that sometimes when I start cutting and pasting a bunch of stuff. Let me restart. One not. Okay, so hopefully you guys can see that now. Draw. Choose this pen. Okay, so what I can do now is I can switch to polar. What that means is my limit now is not like X comma Y approaching 0, 0. It's now R is approaching 0. And everywhere I see X squared plus Y squared, I can replace with R squared. Everywhere I see X and Y, I can replace with R cosine theta. And I can replace Y's with R sine theta. This means I now have R cubed cosine squared theta sine theta. What happens now? Well, now I can simplify. R cancels into that. So I have the limit as R approaches 0 of R cosine squared theta sine theta. Now, of course, as my R is approaching 0, this whole thing approaches 0. Boom, limit is 0. Okay. Questions on that? Yeah, if it's a situation where no R's are left, then in many cases, you can actually conclude the limit does not exist. Because you see, as far as the limit is concerned, this guy is this part here. This is some constant as far as the limit is concerned. Constant where the limit as R approaches 0 is concerned. Doesn't make sense to write limit by itself. So let's say all the R's canceled out, which means you were left over with just the cosine squared sine theta, right? Cosine squared theta sine theta. Then the limit as R approaches 0 would just be the result, cosine squared theta times sine theta. Now, it turns out that if that were your answer, then even though the limit thought of that as a constant, it's actually not a constant. For different values of theta, that would return different results. You would then be able to conclude, well, if the limit depends on this function of theta that can give me different outputs, it must mean that the limit does not exist. Because if I approach along a path where my theta is this value, then that would give me a different result than if I approach along a path where my theta gives that value. So yeah, so even if all your R's cancel out, this can still be a thing that gets you to a conclusion. So yeah, so that's using polar coordinates. What happens if the R is in the denominator? Again, this is now a single variable limit. So you will deal with all those situations that could possibly arise in the same way you would have dealt with them in Calc 1. What would you do if there was a 0 in the denominator in Calc 1, right? Apply all those strategies. Here's a good example for that. How about this one? Make this a little bigger. That example. All right, so I want you guys to try to use the polar coordinate strategy. Switch to polar. And tell me what would happen. All right, so you would get the limit as R approaches 0. Then you'd have R squared ln of R squared. All right, so now we're in the single variable case, right? We immediately go from the multivariable case to the single variable case. How would we deal with this integral? What is limit? How do we deal with this limit? What is that limit? We got some D&Es as an answer. It's not 0 times undefined because it's R squared, which means you are approaching, when the R is approaching 0, it is effectively approaching 0 from the right. So you're always plugging in positive values that are getting closer to 0. So what would this approach? This would approach 0 times, what does ln of 0 approach as you're approaching 0 from the right? Ln of x as x approaches 0 from the right. What is that? It's negative infinity. So this is a 0. This is a 0 times infinity indeterminate form. So now you're going to try to have to remember, how did you deal with indeterminate forms, right? So this would be something, if you want to switch to polar coordinates to figure this guy out, now you're going to have to think, well, what did we do with indeterminate forms? You take him to the hospital. Exactly, you do L'Hôpital's rule. Now, once you see an indeterminate form, L'Hôpital, is that you? What do we need to get L'Hôpital's rule to work? It's fine. It's not your fault. It's French, so it doesn't. However you think it's pronounced, it's not pronounced that way anyway. So a lot of people call it la hospital or l'hospital or something like that. No, it's l'hôpital. To be fair, the translation is hospital, but it's not pronounced hospital. Right, so for L'Hopital's rule to work, you need two particular indeterminate forms. You need 0 over 0 or infinity over infinity, which means you need to rewrite this limit so that it is in one of those forms. How do I do that? Right, you can write this as ln of r squared divided by r to the minus 2, and you would realize that that approaches infinity over infinity. Negative, right? This can work with plus or minus, of course. Right, so now I can apply, we can take it to the hospital. And L'Hopital's rule says differentiate the top, which is just going to be 2 over r, over differentiate the bottom, minus 2r to the minus 3. Then we can simplify. So we can have, this would be minus r squared, looks like. And then, yeah, I know exactly what happens to that as r approaches 0. The limit is 0. And again, this is another thing that we can remember. Remember, polynomials move faster than logarithms. So it turns out that the r square is getting close to 0 a lot faster than the ln is getting close to infinity. So the r squared wins out and it goes to 0. But that is how you would do this one. So I think this gives an example that would answer, was it Ash's question more general earlier on? What if we get a 0 in the denominator? Well, what if we get an indeterminate form? What if we get anything? You know how to deal with this. You have been trained for this. You have been preparing for this your entire lives, right? Whatever situation is thrown at you, I know you guys can handle it. You just need to remember your training, okay? Deal with zeros in denominator the way you've always dealt with it. Deal with a 0 times infinity the way you've always dealt with it. Deal with an infinity over infinity the way you've always dealt with it. In general, you want to deal with limits the way you've always dealt with them. I just gave you now, in this class, 2 more techniques that can apply in a multivariable context. But all your single variable strategies, they still apply, and they will always apply. And in principle, they will always apply. So L'Hopital's rule in a multivariable context, though, is actually very difficult. It's not even worth me telling you what the theorem is. But once you can translate it to a single variable context, which switching to polar coordinates can often do, into a nice single variable context, we are now allowed to use L'Hopital's rule, which we learned the single variable version of. Yeah. All right. So yeah, as also, now the next 2 examples are just some silly examples. It's just me wanting to remind you guys of the way things have been, because I know a lot of you have forgotten the way things were. So I just want to remind you that all your old ways of looking at stuff still carry weight. So just because we're looking at a multivariable limit, you see this guy show up. How would you deal with that? Well, I would deal with it the way I dealt with in Calc 1. I can actually plug these guys in. The answer is -1/4. No squeeze theorem necessary. No fanciness, right? This is just, it's just a plug-in. What are you trying to do? I'm in 212. You're treating me like a baby. Show me some respect. You write that. You say the limit is a -1/4, and you're like, a little respect, please. You put that note. Right? So plugging in, still a thing if you're in multivariable. Simplifying, we saw examples of that earlier. Simplifying so that you can plug in, still a thing. So if you have like this limit right here, you can look at that and you should know, I don't have to actually approach like this. This can simplify. So I can factor out the common y. And because I have radical x -1, then I would notice the difference of squares in the numerator. I can cancel these guys. Now, before I couldn't plug in x equals 1 because I would divide by 0, but now I can plug in x equals 1 and I can plug in y equals 2. So this answer is 4. So our Calc 1 principles still work. You can still just plug in the number and get an answer whenever possible. You can still simplify and cancel stuff, get an answer whenever possible. You can switch to polar and it's a single variable limit now. Things like L'Hopital's rule still applies, right? Up here, we factored and canceled stuff to find the limit, right? We couldn't have plugged in from before because we divide by 0. So all those things still work. Okay. Now let's briefly, we're not going to look at it in all its glory, but let's briefly look at continuity in higher dimensions. Move all these guys up. Is that the last example? Okay, so I taught you everything you need to know about limits so far. So just a reminder, don't forget the Calc 1 strategies, the Calc 1 ways, the Calc 1 theorems, they still will apply. Just add on top of that knowledge, the knowledge that I gave you last class. Now let's talk about continuity. Now, continuity intuitively, again, it's a lot of the same thing. And a lot of things that you would imagine a continuous function should behave like, you know, it's going to behave like that in the multivariable context as well. So continuity just means intuitively there's no break, there's no gap, there's no hole, there's no disruption in the function. It kind of smoothly, you can flow through the point and everything will be fine. Technically speaking, what this amounted to is that the limit as you approach the point must equal the output of the function at that point, right? So this was the equation that we had, right? The single variable version was, we know that f of x is continuous at x equals a if the limit as x approaches a of f of x is equal to f of a. In the multivariable context, it's a very similar thing. You're now just approaching a coordinate, but it's the same idea. If the limit of x comma y approaches a comma b of f of xy equals f of a comma b, then it's continuous at that point. If it's continuous, if that equation works everywhere in some region, we can say it's continuous on that region. We can say a function is continuous in general if this equation works for every point in its domain. So we saw the infinity stones from Calc 1, the 6 elementary continuous functions, the function from which we build all functions in calculus. Now, of course, you're going to learn how to build much more complicated ones, but these are the elementary ones, right? Trig functions, polynomials, rational functions, radical functions, exponential functions, logarithm functions, right? And we learned that if we combine continuous functions, we also can get continuous functions. So you add 2 continuous functions together, the result is continuous. You subtract them, it's continuous. You multiply them, it's continuous. If you divide 2 continuous functions, the result is continuous as long as you're not dividing by 0. So you can combine continuous functions using arithmetic operations, and as long as the arithmetic operations themselves don't introduce any issues, like a division could introduce the possibility to divide by 0. As long as no issues are introduced by the arithmetic itself, the resulting function is going to be continuous. That is still true. Even in the multivariable context, I can combine multivariable functions in various ways. And if the original functions were continuous, the result is going to be continuous. So all of that, still the same thing. The different thing here is, again, what a limit means and what we need to get a limit to work out is much more difficult in the multivariable context. We have to consider an infinite number of directions as opposed to just the left and right. So take what you know about continuity from Calc 1 and add it to the fact that you finding the limit part of that process becomes a little bit more difficult, a little bit more nuanced, okay? But everything else otherwise you kind of know already, right? You kind of know the 3 things that has to happen for a function to be continuous, the checklist that you'd have to go through Again, this is just me rewriting some Calc 1 strategies that I went over with my class in a multivariable context. Some things that we automatically know, like how to combine continuous functions, limits pass through continuous functions, etc. That one might be a little bit, once I show you, you'll know what I'm talking about, but sometimes people don't know what I mean when I just say that. So this means like if I'm taking the limit of like the sign of some function, then it's the same as the sign of the limit of the function, right? So the limit, the LIM can pass through the continuous function. If I'm taking the limit of e to some function, it's the same as e to the limit of the function because e to the x is continuous. So limits can pass through them. Add two continuous functions to get a continuous function and all that good stuff, still true. The extreme value theorem still holds, which means if you have a continuous function on a closed interval, then it's guaranteed to attain an absolute max and min. In the multivariable context, this changes. You no longer have intervals. Now you have regions in two space. If I can say, if this function is continuous on the boundary of this rectangle, then it will attain its absolute max and min within that rectangle. That's kind of how you want to think about it. You bump the dimensions up. So we don't just talk about intervals anymore. But in principle, something like the extreme value theorem still holds. And you're going to deal with that in 213. So you need to, and of course, you will need to remember the Calc 1 version of how to check for absolute max and mins in order to do the multivariable Calc version. But that's going to be a thing you're going to check, and you're going to realize that checking absolute max and mins in Calc 3 is way more annoying than it was in Calc 1, but I'll wait for you guys to see that. That being said, let's just wrap up with some silly examples just to remind you. So nothing new here in terms of tips and tricks to show you. We're just going to apply our old knowledge, our new knowledge with old principles to kind of get through some problems. So I don't even think it's kind of worth me wasting the time asking you guys about this. So I'll just go through these and kind of discuss them with you. So you see something like this and someone asks, where is it continuous? And you just realize, well, this is a ratio of polynomials. Polynomials are continuous everywhere. So the division is going to be continuous everywhere unless I divide by 0. So we know that this is continuous as long as x minus y is not equal to 0. This means as long as x is not equal to y. So I would say continuous on the set of all xy such that x is not equal to y. So as long as we're not on the plane x equals y, that guy is continuous. Okay, and that shouldn't be cause for alarm, hopefully. This one, again, not continuous as long as the denominator is not 0. So continuous as long as x squared plus y squared is not equal to 0. This means x not equal to 0 and y not equal to 0 at the same time, because that's the only way you can get the sum of squares to be 0. The both squares would have to be 0. So this means 0, 0 is not in the domain. So then you would be able to say it's continuous on this set, the set of all x comma y, such that you're not at the origin. As long as you're not at the origin, this guy is going to be continuous. Okay, that's the same guy. We ended his whole career. Now we're just like talking about where he's continuous. He's continuous everywhere except the origin. Now let's actually tweak things a little bit. Where is this guy continuous? So this is another thing that you would have seen in Calc 1, where someone goes and tries to fill in the bad point. So we know it's not continuous at the origin. So at the origin, we redefine the function to be something else. Is it now continuous everywhere? Well, it depends on what you filled in that thing. right? So here you'd realize if we're not at 0, 0, we're fine. So check 0, 0. Right, we need to see if I take the limit as I approach 0, 0 of the function, do I get f evaluated at 0, 0? Is this equation true? Now, the limit of f equals 0, we showed this earlier in several ways. And f of 0, 0 equals by definition of the function. So this guy is actually continuous everywhere. And you can still use that language, continuous everywhere. I.e., you can say continuous on R2, or i.e., you can say continuous on the set of all x comma y such that x is in R, y is in R. Right? So that guy actually works everywhere. So you can actually fill in the point and create a continuous function. And I showed the, by the way, ETW. Check this out. I gave the other class this. Go here to this website, which I'll leave the link in the thing, you can actually, let me actually show you. Okay. You're all seeing my browser, right? Yeah, all right. So you can actually plot 3D things. Now there are tons of websites that you can do this. Let's look at this guy that we defeated multiple ways. He actually looks like this. Right? Now the origin is right here. It's in the middle of where all this craziness is going on, right? And it turns out there's a hole there, but you can't really see it from this view. Right? If you go to this one, this is another website, and I can type that in. X squared times y divided by x squared plus y squared. There's the guy again, and you can see where the origin is. And it turns out that there's really a hole there, but you can fill it in and make it continuous. So that's our guy. So and let me copy a picture over here. Now you know what this guy looks like. Now this is like a heated map, so red means highest elevation, blue is lowest elevation. If you were to find the absolute max and min of this function, it would occur over here towards where x and y are their largest or their smallest, to this side. So that's what this function looks like. This guy here, again, somewhat obvious how we would deal with that guy. The sine is a continuous function, and x is a continuous function, y is a continuous function. So as long as you're not divided by 0, this is going to be continuous. So you just know continuous as long as y not equal to 0. So this means continuous on set of all x comma y such that y is not equal to 0. So as long as you're not touching everywhere but the xz plane. So as long as you're not touching the xz plane, you're fine. And you might ask the question, can we actually fix it? Can we fix this? Right? Meaning, can I define it at points where y equals 0 to actually make it work out? And it turns out the answer would be no. And if you wanted to see just how much trouble this guy is in, that's him. So a lot of craziness is going on, right? As you approach the origin, you can kind of see, yeah, you're not going to get that guy to work right there, right? The origin is up in here somewhere. It's like a really big gap, right? You can't fill that in with one point, right? So we're kind of out of luck with this guy. Can we fill him in here? So that's the guy. Go slower. Slow it down. Slow motion for me. Okay, there you go. That's what this guy looks like. Crazy function. You'll be dealing with those guys in 213, so I'm not going to spoil all the fun for you. So yeah, so can we fix it? No, we can't. Calc 3 is going to be a lot of fun, especially with how we've now made Calc 2, where you actually already get introduced to the 3D world in Calc 2. Calc 3 should actually be a lot easier to grasp now. I still feel like this is the hardest course in the sequence now. As long as you remember your training grasshoppers and you remember the fundamentals, you will be fine. I'm just getting a picture here. Paparazzi. I don't know how likely it is I'm going to teach Calc 3 anytime soon. I think in the summer they kind of want people. So unless someone who's teaching Calc 2 now drops out for the summer, I think they want to keep the people who are teaching the classes in the spring to teach the same class in the summer, because it's going to be online and they don't want people to do whole entire new preps. Yeah, so I think we can end here. So I'm not even going to do any more examples here. I'm just going to mention some facts. So here's the nice thing, which I mentioned earlier today, and it is true. I don't have any more examples, right? Okay, cool. I mentioned earlier today, and it is indeed true, that multivariable calculus opens a lot of doors in the sense that once you learn how things work in a multivariable calculus context, you can extrapolate it to a lot larger context. So in multivariable calculus, we're going to do 99% of our work in 3 dimensions. And obviously jumping from a 2-dimensional world to a 3-dimensional world has a lot of changes, right? Even our notation changes. X equals Y was a line, now it's a plane, right? Limits, we only cared about 2 directions. Now we have to care about infinite directions, right? So there are a lot of things in jumping from the 2D world to the 3D world that actually change conceptually. So single variable calculus has a different mindset, different thought processes than multivariable calculus. The good thing is, once you learn how things work in 3D, it's a lot easier to figure out how things will work in 4D, 5D, 12D, ND, then the jump is going to be a lot less severe, mathematically speaking. Now, granted, we can't visualize anything in higher dimensions. I don't know what anything looks like in 4D or higher D. Like, we won't be able to visualize it, but mathematically, it's very easy to make the extension, right? To move from 3D to 4D, the only thing I do is change all my vectors from 3 components to 4 components, but the math is going to work out the same, right? I don't need to, it's going to be very similar, right? So you're going to be able to extend yourself into many dimensions once you really learn how to work in 3 dimensions. Jumping to higher dimensions and into more exotic situations is going to be a lot easier. So that being said, vectors are going to be very important. Vector functions are going to be very important. Once you learn how to think in terms of vectors, then jumping to a higher dimension is a matter of adding a component to your vector. And the math works out the same way it did before, right? So you won't have a drastic change or a drastic reformulation going into higher dimensions. That being said, I just wanted you to see what the definition, the precise definition of a limit would look like in a higher dimension. It's just that instead of x comma y is approaching something for a limit, you have an entire coordinate of variables, x1 comma x2 comma dot 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 all the way up to xn, where all of these guys are independent variables. And then you want to approach a coordinate, a1 comma a2 comma dot 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 all the way up to an. These are just numbers that you put in a coordinate. And the limit definition would look exactly the same, except you replace the x and the a with vectors. And how you would work in this context is exactly how you worked in limits in the context of this class and last class. Conceptually, nothing else is going to change. You still have to approach from infinite directions. The same squeeze theorem is going to work. Once we learn all the things from at this point, jumping to higher dimensions is going to be very similar. Your algebra you have a lot more algebra to crunch through, but there's no real new concepts. You just kind of add more of the same. So I thought I just wanted you to see what that would look like. And we are going to stop there. So that ends this section. That ends us dealing with limits in higher dimensions. We now know how to show that they don't exist. We now know how to show that they do exist. And we know how to use several techniques to do it, including some techniques that pull us back to the good old days of Calc 1, or the bad old days, because Calc 1 was too easy. I'm sure you all feel the same. That's it. We're going to wrap up here. So again, announcements. Final is on Thursday, May 21st, 3:30 to 5:45. If you have 3 finals, you can move the middle one. You need to reach out to the instructor for that, though. We will have class tomorrow, 2 to 4 p.m. I have a final in the morning, but it will be done by that time. And I will post by then a review for the test next week. And we will actually do a trial run of a Blackboard test for you to see what that looks like. Yeah, I think that's okay. Yeah, the grading is going to be ASAP. I'll try to get the grades feedback ASAP. I don't know when exactly that's going to happen. Can't promise you a day, but as soon as possible. And what else? I don't know what I'm teaching in the summer. I applied to teach chances are I'm going to be teaching this class again. It's from the sounds of it. And yeah, I think we'll wrap up there. So that being said, we'll stop there, and I will see you guys in the next one. So stay safe and practice your math. Remember you're training grasshoppers, so if you forgot about limits and all that stuff from Calc 1, it's worth going over it a little bit. You can watch my Calc 1 videos, practice some of the examples I did, and it should get your mindset back in that mode. That being said, we'll end right there. Thank you guys for joining, and all right, yes, you too. Have a nice day. Ciao.